Hi, everyone. As you all asked, I will record the H1 tutorial, just going step by step for it, so people can look at it, and if we will manage to install the packages for Python notebooks to work with Python 3, for those whom doesn't work, you can go back to this tutorial and maybe check it out, try to run it for yourself. But for those who couldn't join us today due to the power outage or who cannot run the notebooks, I will record now the session with some guidance which you can get from the notebook. So Melvin mentioned to me that you didn't look in the detail at the data yet, that you were more focusing on the technical side. So I wanted to show you first how H1 data looks like. Where do we have a mission? What do we call a mission? What do we have? What do we call noise, and what do we call sigma, and what is the free sigma detection? So for this, first I want to share my screen in order to show you how the H1 data cube looks like. So from the lecture, as you saw, when H1 is observed with interferometer, you have many channel maps at particular frequency, and you're looking at them, and then you're trying to find your emission at every frequency. And here we see an example of one channel map at this frequency in Hertz. And here is what we call noise. We don't see much emission, we see some structures, but it's pretty much homogeneous. And in the ideal world, ideal noise should be homogeneous. So basically you have like your white screen when TV channel is not working. However, there are many data reduction artifacts when dealing with the H1 data and in general radio data. And you can, for example, see here, you see some stripes of residual noise, which make the map a little bit not homogeneous. And if you will check the pixel value here, so here you see the value, and if I put an error on it, there is a value which you can see, and these black dots, they are all negative values. And for example, these very bright white dots, they are positive values. And if we start to scroll through our data cube, we see that second channel, for example, has more negative pixels, negative values than the previous channel had. And then we scroll, and here we see clearly that there is something is different, that it's not only noise in this channel, but there is something what we call emission. And how we know that it is emission? The intensity is much larger than the values of the noise around it. So for example, I will put here the arrow to the very bright pixel, and the value is 0.0056. And if I will put it somewhere here, you see it's either negative or extremely low number. So this is our signal, real emission. Everything around this signal is noise. We can measure the properties of this noise. For example, if we will sum up all pixel values within this map, in ideal world, you will have only emission, because the noise will cancel itself, because the noise would be, the amount of positives would be equal to amount of negatives. However, it is not always the case, and we need to understand the properties of our noise in order to assume it as an error on our emission. And this is one of these properties is called RMS, or root mean square, and it's basically the average of your noise value. And it's like if you will take an average minus emission, for example, average in this channel of everything, that would be your RMS. So the value, some pixels will cancel itself because some will be positive, some negative, but some little residue will stay. And this is what we call RMS. However, in radio astronomy, we assume in H1, we assume that noise is Gaussian. So basically you have Gaussian distribution peaks of the noise, and therefore we calculate RMS as a standard deviation of this Gaussian. When I want to understand the properties of my emission and basically how strong is my signal, because here we definitely see that we have a signal. However, we need to understand how strong is it. That's why we need to compare the intensity of our signal in comparison to the noise around it. And for this, we calculate the standard deviation of, for example, our noise region minus emission. For example, we have emission here, and we select a region of noise just around emission, not including emission, and we calculate the standard deviation or the average of this noise, and we will have a value. If we are talking about just one channel, that would be your so-called sigma, and then you can calculate just the pixel which have the emission, and then you will end up to a value, and then the difference of these values, you will say how many sigmas is your detection. So how much larger your detection signal than your mean noise value. And we consider the signal to be reliable and signal and not noise when it is at least 3 sigma. So everything above 3 sigma we consider as a real detection, and everything which is below 3 sigma is either buried than noise, but we cannot say exactly that the property, what is the property that this signal, or is there a signal in general. So when we are dealing, this is in the example of one channel. However, when we are dealing with the whole data cube, as you see, we scroll through different channels, the noise properties might change depending on the channel. And therefore, for this reason, we select a region outside of emission, which will not have emission in either of the channels. And for our tutorial, I selected this region as the bottom right, as the emission-free region for every channel. And we calculate first, we calculate RMS as a standard deviation of this region in every channel. And then we take a mean of this value. So we will have RMS per channel, and then we take a mean. And this would be our sigma for the entire data cube. And you will see further why do we need it and what do we do with it. Here now we will, I hope it's a little bit more clear now, but you will see further how does it work when we progress through the tutorial. I'm sorry, I need to pause for a second. Okay, so this is our tutorial, and we can progress through it one cell at a time. So first, you already worked with the notebooks, you know how it works. First, we import all the useful packages that we would need. And now we have a bunch of useful constants we use for when we analyze H1 data, like H1 rest frequency, Hubble constant, or speed of light. So we just put them in. Now the data cube, which you just saw, we can import here using the spectral cube package. And we can look for example, at the dimensions of this cube, we see that it's all in pixels. We see that in X direction, it's 400 pixels, and Y direction, it's 400 pixels, and it has 12 channels in frequency. We can identify the central channel, the central frequency of our source just by looking, for example, at the data cube. So it's where your galaxy the most elongated, or just calculating the mean of the range. So the frequency, the observed frequency, or the central frequency of our source is as follows. We also ping it in. Then we can look at the header of our data cube, and header tells us a lot of information about how data were reduced, what are the units of the axis, what is the size of a pixel in arcseconds, what is the size of the observed PSF, or the synthesized beam, how we call it, and all those things, and some of them we indeed need for further calculations. We can look at the header. Here is all the information it has. And here we can go and extract the values from the header, which we will need to use for our further analysis. For example, here I'm extracting the major and minor axis of the synthesized beam, and all values here are in degrees, so you need to multiply it by 3600 to get it in arcseconds. BPA is the position angle of the synthesized beam. dpx is the amount of arcseconds per pixel. And df is your frequency resolution. So the size, the width of a channel. So the channel width or the frequency resolution. And we can run it here. And for example, here we ask us to plot the major and minor axis of the beam and the frequency resolution, and we have it here. Further, we can move on to calculate useful parameters, which we will need. And first of them is the parameter to convert our flux units from Jansky per beam to Jansky. Because when we observe in our data, every pixel has an intensity value, which is the units of Jansky per your synthesized beam, which has major and minor axis derived here. So in order to convert from Jansky to beam, we need to know the area of the beam in arcseconds. However, all our data are in pixels, and we know that there is 2 arcseconds per pixel. So we also need to calculate the amount of pixels within the beam area in order to be able to convert from Jansky per beam to Jansky. Next, what we need to know is the systemic velocity of our source, because our data cube is at frequency. So by using the formula, we can convert from frequencies to velocities just by knowing the rest frequency of each one, which we imported as the first useful constant, and the observed frequency of your source, which we calculated. Next, we can calculate the distance by dividing this velocity by Hubble constant, and distance we will need when we will calculate the H1 mass of the source. Then we can also calculate the redshift just to know at how far our galaxy is, what redshift is it. For us, it's not very important now because it's pretty nearby. And then we also can convert the channel width from hertz, which we extracted from the header, to channel width in kilometers per second, because we will need it in order to calculate our flux density, which is usually presented in units of Jansky kilometers per second. And here we can see that our observed frequency of the source is 2242 kilometers per second. Or for example, we can ask what is the redshift of our source, and the redshift is the following. When we derive all these properties, we now can convert the third axis of our cube from hertz to kilometers per second, just because we usually work in kilometers per second. The velocity map is in kilometers per second. The rotation curves of galaxies are in kilometers per second. So there is a nice conversion. visit the spectral cube package. So we just press there, and now our cube, the third axis of it, would be not in hertz, but in kilometers per second. Next, we can calculate the spectrum of our data. What is the spectrum? Spectrum is the sum of all pixel values within each channel, and we present spectrum as a function of intensity, so a sum of all pixel values, as a function of velocity, so in each channel, what is the intensity of the sum of all pixels. So for this, we derive sum of axis 1 and 2, so of axis array and deck, and we will obtain spectrum in Jansky per beam in original values. Therefore, we will multiply it by this component, which we calculated previously, in order to have the values of our spectrum not in Jansky per beam anymore, but just in Jansky. As in here. And now we can look at the values of our spectrum to understand. In general, is it good, is it bad, is everything worked out? Next, we can represent each velocity channel just as an array of each velocity. So for this, we just do axis value of our cube. And here we see that our cube is ranging from 2500 to 2000 kilometers per second. And having our spectrum in Jansky and our array of velocity, we can examine our spectrum. And here it's the simple plotting, and you can save this plot, for example, wherever you want. So we look at this and we see something like this. We see that indeed in every channel the amounts are positive. However, it doesn't look very nice. It's very patchy. It's not very symmetric. So it doesn't look like a nice global H1 profile of the source. And why is that? It is because, as I said, we calculated the sum of every pixel in the data cube, including emission and including noise. And as I said in the beginning, in ideal world, that would be okay because the noise would cancel each other and then you would have only the values of emission. However, it's not always the case, and there are sometimes more negative, sometimes more positive noise peaks, which affect the overall value of the spectrum. So additionally, we see, and I again will move to here. Additionally, you see that here emission is not particularly, in this channel emission is pretty bright. But for example, when you go here, you see that there is like a little tail of emission, which we can see by eye because human eyes are extremely trained to recognize patterns. But however, if we will calculate our sigma of noise here, this tail will be pretty close to the sigma and it will not make the cut of 3 sigma. So most likely, if we will calculate the RMS as I described to you before, and then we will leave only 3 sigma signal in the cube, this tail is not going to make it in. And so we will lose a very important piece of information regarding the morphology of our galaxy. So in order for this not to happen, we convolve our data with a larger synthesized beam. So basically, you will see the difference now, but basically now imagine that you have your frame and you take like a larger circle and you just make it smoother. It's something what your, for example, mobile camera does sometimes when you do pictures, and then it's making the features smoother. We do exactly this for our data cube in order to bring emission up and the noise down, and I will show you how it looks in a second. So for this to be able to convolve our original cube with the smooth bigger beam, we need to define what size of the new beam we want. So original size of our beam is 12 by 10 arc seconds. Here I chose 20 by 20 arc seconds. You will see the difference soon, but believe me, it's a good number because you don't want to smooth too much to lose all features, but you want to smooth just enough in order to bring important emission features above the noise level. So we define the beam size, and then we create a new cube where we ask our old cube to be convolved with the new beam, and then we can save it. This exercise takes a little bit of time. And now, since we saved it, we can look at the new smooth cube, how it looks like. Here I can ask for a new frame. Here I will keep the original resolution cube, and I will open the new smooth cube. And you see immediately the difference. The structure of the noise popped up here, and everything is like more blurry. So if we will go through it, you will immediately see the difference. So this is the same channel. This is a cubelet of our original resolution, 12 by 10 arc seconds, and this is the cubelet of new smoothed one. So you immediately see that this tail of emission is much more prominent and stands out much more in comparison to the background noise. And this is exactly the reason why we do this exercise, just for our emission to pop up a little bit more. Here you also see, for example, we look at this channel, and here you see that the emission stands out much further than the noise in comparison to this cube. However, you also see that little fine structures and details will be lost, and you will end up just with sort of blob of emission. So the further in resolution you smooth, the more you lose features. Like, for example, if you keep smoothing your face in a photograph, you will not see a nose or a mouth, but sometimes we want to have these features, but just smooth our wrinkles a little bit. So this is the same principle. So we always need to smooth very carefully. So we don't want to lose our resolution, but we want to keep this low column density emission, which we otherwise don't see on highly resolved cube. For this, we create a mask using this smoothed cube. We do exactly as I described in the beginning. We take the same box and calculate its RMS. And then we take this cube and we ask, remove everything which is below 3 sigma and leave only 3 sigma signal inside our cube. And this is exactly what we are doing in the next step of the tutorial. We create a little subcube of that region in the corner, and we calculate its RMS as standard deviation, which is mean if your noise distribution is Gaussian. And then we calculate sigma as a mean of RMS in every channel. And here we can, for example, print our RMS. It's very small, but again, it's not 0, which is important. And we can print our sigma. And this is 1 sigma. And we remember that we consider a signal everything which is above 3 of this value. And we calculated this on our smooth cube, the one which is with the smooth features. So then we can create what we call a mask. And mask, it's exactly this. We take this cube and we say that the mask is this cube values everything which is bigger than 3 sigma. That's how we create the mask. Mask is done. However, if you will keep mask as it is, you will lose the important resolved features because your cube is too smooth. So you want to have the best of both and keep emission where it should be, the region of emission, but you want to keep it on this original resolution. It means that we can do it by applying the mask which we created from the smooth cube into original cube. So all regions which are higher than 3 emissions will be saved, but then we transfer those regions to original resolution cube. It means that that tail of low column of low H1 emission, it will be preserved just because mask accounts for it, because mask is done from the smooth cube. I will show you what it exactly means, but this is what we do in this cell. We create a mask cube, which is this cubelet of original resolution, but now we say with mask, and we include mask which was done based on the smooth cube. And then we can write down our mask cube and see how it will look like. We can go here, we say frame new. So now we have our third window and we open our mask cube, which I saved, I think, in the one directory. Here is our mask cube. And you see, first channel has nothing in it because there was no signal above 3 sigma. We go to this next channel and it's also still nothing in it. And we go to this channel and we already see that the tail is being preserved and the tail is of high. So this tail, which we saw here barely, and this tail, which we see here, these pieces of the tail made it to be above 3 sigma in this cube. If we would do it in this cube, none of the tail features would make it. We can go here of emission. And here again, we see only emission. It is the size of the emission of this cube, but it is of resolution of original cube. And this is very important. So you can keep your low column density emission. It is larger, but it is of original resolution. So this is what we call masking. And if we will keep scrolling through the mask cube, you will see, of course, there are a couple of noise peaks here. As I said, noise is not perfect in real data, and some noise will be higher than 3 sigma. But overall, you see that this cube consists only of the emission of this galaxy. And for example, this tail, we can barely see it here in the original resolution, but we preserved its shape, we kept it because we used masked of the smooth cube. And here we end up, and here you even see the little companion, which is also above 3 sigma, which made it into the mask, meaning that this source, this little blob up here, it's a real galaxy, it's a real source. And we end up with a cube which has only H1 emission in it and doesn't have all this noise. So what we can do now, we can use this cube in order to create spectrum just of detected F1 emission without contribution of the noise. And this is exactly what we are doing here. We call it spectrum new in Jansky. Now we use this mask cube, which we created here, create spectrum exactly like previous step, multiply it by our conversion factor from Jansky per beam to Jansky. We can also look at its values. And now we can examine both spectra which we derived from the original cube, including all the noise, and spectrum which we have now only from emission of the galaxy. And here you see the difference. So the orange now is the first spectrum which we derived from the cube which had everything in it, and emission and noise garbage. And the second spectrum, it's only the spectrum of the emission of our masked cube where all the noise is removed and only emission stayed there. And now you see huge difference and huge improvement. You see, for example, here the blue emission was suppressed a lot over these channels by the negative noise. The same is happening here. So basically we recovered our flux by applying the mask and by looking at the intensity only of the source without the noise. Here we also see the big improvement of the shape. Now it looks exactly like global H1 profile. The two double horns indicate that the galaxy is rotating. And here, remember, we calculated what should be our central velocity or systemic velocity of the galaxy, which is about 2250. Around here. And so we know that this is a velocity with which this galaxy basically flying in the space away from us. So now we know its velocity. It's indeed in the middle of this global H1 profile. After we calculated our global H1 profile, our intensity from the nicely masked cube, we can calculate the H1 mass of this source. How do we do it? We need to sum up all values under this blue curve. So we call it flux total. So it will be the total flux of our source. So here we have flux as a function of velocity. And if we integrate under this blue curve, we will have total flux. So total flux is basically NumPy summation that we sum up all the values of this new spectrum. Then we can calculate the flux density. The flux density is your total flux multiplied by the channel width, and this is exactly what we use to calculate the H1 mass. So we take flux total and we multiply it by the channel width in kilometers per second, which we calculated previously. And by knowing distance and flux density, we can calculate the H1 mass of our galaxy. Here, we can print the values and we see that the H1 mass of our galaxy is 1.8 to 10 to the 10 solar masses. So it's a pretty massive spiral. And this is just the log of our galaxy. And now knowing the log, we can do this exercise. We can, since we know the H1 mass, there is, you saw in the lectures, there is a linear relation between the H1 mass and the size of the H1 diameter. So just by knowing mass, you can now go and calculate what will be the diameter of H1 disk of this galaxy. However, you saw in the data cube that our galaxy consists, that our data cube consists not only on one source, not only of the main galaxy, but also of the teeny little dwarf next to it. So in order for us to understand the details of how this mass is distributed within the galactic disk, because now we know just one value and we saw the spectra, but we would like to see what is the intensity of the arms and what is the density of the little component, we can create the so-called moment zero map or H1 intensity map, where basically you will create a map of every pixel combined together, not as a function anymore of every channel, but just as a 2D map. So we run it here. And as we discussed in the lecture, usually we discuss the H1 intensity not in Jansky, but in atoms per square centimeter. So how many atoms of neutral hydrogen are there in the square centimeter of the galaxy distribution? So we can convert our moment zero map, which is now in Jansky per beam, to atoms in square centimeter using this formula. And you saw in the lectures that we can not only discuss the atoms per square centimeters, but also we can discuss H1 intensity in terms of the surface mass density, which we calculate in stellar mass as a square parsec. So if you want, you can do the same exercise just by using moment zero map. Just by using atoms, you can convert them to surface mass density. But here we will not do this. You can do it yourself if you like. But now we have our H1 intensity map and we would like to visualize it. Again, here is a little code for this and you can save your figure. Here is a lot of warnings, don't pay attention at them. And ta-da! Here we see the H1 intensity map. We see that there is a nice galaxy. This is the tail we saved by smoothing and masking. You still see that there is a little bit of noise peaks, but at least it's not the whole map is covered in noise. And here is our little companion. The bar here is in atoms per square centimeters. So it's, for example, the peak is 3.5, 10 to the power of 21 atoms per square centimeters. And here already you can analyze a map and analyze what you see. For example, you see that the disk, that the galaxy is not particularly disky, but it has these beautiful symmetric tidal arms. One is brighter than another one, which are probably induced by the presence of the little companion over here. You also see that the brighter it is, the higher column densities there are. So column density means atoms per square centimeters. So we see in the centers there are many more atoms, much higher column densities, which decline to the outskirts, which are much lower here. So it's already 5 10 to the 20 instead of 3.5 10 to the 21. And we see that the component is also very similar color as the outskirts, meaning that it is a dwarf and it's also not very massive, doesn't have very high column densities. So here I just posted some questions which are based on the lecture, because in the lecture I've told you that each one is the first tracer of environment and the first to react if something is going on in the vicinity of the galaxy. And this is exactly what we see here, that the H1 disk became perturbed due to little companions, so they gravitationally interacting, and probably the environment of this is a minor merger. So these galaxies are gonna merge and big one soon is gonna eat up a little one and acquire it. So this is what we already can say about one object just by analyzing a data cube. Next, we can look not only at H1 intensity map, but as I showed you in the lectures, also at H1 velocity map. So we will understand how fast this galaxy rotates. For this, again, we need to now not moment zero, but moment one map, the velocity moment. We run it through. Some warnings here. And again, we can plot it. And if you want, you can also save it. And here is how our velocity map looks like. And here again, I wrote you a couple of questions. You can go through them yourself and see that you understand how it works. Please look at the lectures. But for example, is this galaxy regularly rotating? In order to answer this, we need to look Are these things symmetrically distributed, the red and the blue? Yes, pretty much. We see that they are pretty much symmetrical and the contours are symmetrical. So this galaxy is rotating and pretty regularly. With the black line here, I show the systemic velocity, which we already calculated from the global H1 profile. And here it will manifest itself just in the middle of your map. And then the blue one will be the side approaching, so the side of the galaxy which rotates towards you, and the red one is the side of the galaxy which rotates away from you. How do we know it? We know that this systemic velocity is about 2250. We can subtract this systemic velocity and just understand, because this is how fast the galaxy flows away from us. And then we will end up with around 150 kilometers on one side and minus 150 kilometers on the other side. So minus says that galaxy side is blue shifted, therefore blue, so it goes towards you. And plus says that the galaxy side rotates away from you with the velocity of 150 kilometers per second. We can also now look, for example, at the color of companion and see that it is much darker than any of the gradients here of the galaxy. So we know that the component, if the systemic velocity of the galaxy is 2250, the systemic velocity of the component is around 2100. So the little galaxy moves away from us a little bit slower, just with 2100 kilometers per second. By knowing this, we can calculate the redshift of this little galaxy, little companion. We can calculate its distance from us, and we, for example, can compare the distance of the companion and the distance of the main galaxy, and we can derive the distance, for example, between them. If you're interested, please do these exercises. And that was all about the tutorial. I wanted to make it as realistic and as practical as possible, so you see what H1 astronomers basically doing in the real life to hundreds of galaxies. Thank you very much.